Continuing from yesterday, we looked into the simple dynamical models, and the last thing we needed to find our equation was causality. Should be here somewhere. Thank you. Here we go. Causality. So, causality, that was sort of finding out what causes what. So I think the easiest way here will be just doing some examples. The camera, I don't see that one, I think. No, it doesn't. There. Let us do an example. From the ceiling, we take a mass and we hang it up there with a spring and a damper in parallel. So here you have mass, you will have a spring stiffness K, damper R, like that. Linear damper, so it's a force then proportional to the velocity. And we have gravity acting down, and positive direction. Well, why not take it downwards? Find the equation of motion, the state equation for that problem. First of all, we translate M, that is an inertance, spring stiffness K, that is 1 divided by C, R for resistance, that's okay. So now let us try to make a bond graph of this problem. I start with the mass. The mass, that is one solid object moving with its own velocity. So I will use a one junction on top of him. And this one junction has mass attached to it, so I just hook on the inertance directly. Then he branches to a damper and a spring. How did we insert such elements? Well, it's the same force on each side of these elements. Same force here, same force here. Hence, you will insert them using a zero junction. So here you insert the resistance, here you will insert the spring. And then they are joined in the ceiling up here to another one junction, which is not moving. So here the velocity x dot equals 0. Now we are missing something. Where's the gravity? Where is the gravity? Well, the gravity is attacking what? It's attacking the mass and only the mass. So for this one junction here, he is attacked by a source. What kind of source? Well, gravity will provide a force, an ideal force. So this is an effort source. That is the raw bond graph. Now simplify. Simplify it as much as we can. Well, we start up here. We have a solid wall not moving. Hence, the power for these two bonds is going to be 0. The velocity is 0. The force can be whatever it wants. It's no work done here, no power. So these two can be removed. Then these zeros, they have only 2 bonds. And for a junction with only 2 bonds, it's not a junction anymore. Remove, remove. Okay, then it's fairly simple. I have 1 junction, and then I have 4 bonds. That's it. So simplified. He should then look something like this. We have a 1 junction, and here we have gravity attacking, and here inertance, up here resistance, and finally a spring. So that's the simplified bond graph. Now apply the causal strokes, the causality. What was the rule there? Always start with the sources. That's the first step. And an effort source, well, he provides us with gravity. So it's the gravity then attacking this system. So the causal stroke has to be there. Okay, that doesn't dictate anything. What was the rule about the 1 junction? Well, a 1 junction, common flow, he should have all strokes towards him except 1. And the one where we are missing the stroke, that's where we find the flow that dictates what the flow should be on all these bonds, the common flow. So here we can't really tell, but I have a C and an I element, so there I choose the integral causal form, as long as I have somebody free. Start with the C element, the spring. What was the desired stroke there? Well, the integral integral causal stroke should then be like this for a C element. Now he is on the integral form, the form we like it. It still doesn't help. We still have a choice here. One of these two has to be away. Fortunately, I still have an I element, so I can still choose. For an R element, you are not allowed to choose. That's forbidden. So he should pop out automatically. But an C and an I element, you can still choose. So here, of course, I also choose the integral causal stroke. That should be like this. Now I have found the 1 stroke away from the 1 junction, hence the last stroke has to be like that. So yes, this is a causal system. All the bonds, they get the causal stroke. I'm not missing anything, and also all my energy storage elements, all I and C, are on the integral form. So this is just nice. Now finding the equations. We have a force from the source. So here I can write an effort mg. That's gravity force. On the other side, from a source, we are not interested in the flow there, so just write an x. For the C and the I element on the integral form, when you have them on the correct form, you can immediately do the following. Here you now have a q dot with a circle around, and on the other side as an effort, only q, time integral of q, divided by c. While the inertance, you will have the effort called a p dot, and also here with a circle around it, and beneath as the flow, p over I. So the circle now indicates a differential equation. So now we can tell immediately this is a second order system. Furthermore, we have now found the flow responsible for this one junction. It is where we are missing a stroke, hence it's going to be P over I. This is the flow. So down here I've just set an X. I could have set P over I here if I liked, if I wanted to, but normally we don't care about him. But here also I have the flow, P divided by I. And also here. But now this position is taken. It's already a Q dot there. Okay, but then they have to be equal. So Q dot equals P over I. So that's my first differential equation here. Okay, we still are missing one effort here to have this bond graph completely annotated. What effort do we have here? Well, now I know the flow. Then it's fairly easy with a linear damper. The effort here must be the resistance multiplied with the flow. Now this bond graph is completely annotated. All bonds has gotten an effort and a flow. What about the equations? It should be two. I found one. What about the other one? Well, we had that rule around for a one junction. The flow is common, okay, but the sum of the effort has to be 0. So we sum up all the efforts around this one junction. So we can write it like this. What comes in must go out. The only one entering is the gravity. So here I will have mg equals what goes out. What goes out? Q over C. I have an damping force here, R multiplied with P over I. And finally here I have something called a P dot. And of course we rewrite that one immediately to P dot equals, and then he will equal mg minus Q over C minus R P over I. So here is equation number 1, here is equation number 2. Any questions so far? That's okay. Okay, then we don't need the bond graph anymore. Can remove this one. So now in a MATLAB script, we can easily program these two, the two derivatives, and then finding Q and P as a function of time. So the solution is going to be Q as a function of time and P as a function of time. These are the generic names. So Q dot for a generic flow, P dot for a generic effort. But now in the end we sort of look back to our real problem. What do we want? Well, I actually want to find the position here. Where is he located? And now the position, well, Q dot, that's the velocity. So Q alone is a position. So if you like, you can call this one X or Y or something. What about P dot? Well, P alone. Well, that would now be mass times velocity, because a P dot, that's mass times acceleration. So this one is mass times velocity. So maybe we would have liked to plot not the momentum here, but only the velocity. So you divide by m on the entire equation. That's typically what you would have done. Let's just check now for Newton's second law. As a check. How can we control this? Well, I have two first-order equations, differential equations. Rewrite them to one single equation. How can you do that? Well, take the first one and take the time derivative of the equation. Then we will look something like this. Q double dot equals P dot divided by I. P dot divided by I. Well, I have a P dot here. And then just divide by the inertance. What do you get? It will be something like this. Gravity minus Q divided by CI minus R, and then P over I squared. So that should be the equation. And now if you translate back to the physical quantities, gravity Q, that is the position x. The C, that was the reciprocal of the spring stiffness. So here I will have K divided by the mass m, and here resistance multiplied with what is P? P, that is mass times velocity. Velocity, that is x dot, and then the mass is dropped from the momentum here, but I still have a mass, an additional mass. So this actually is the equation. And of course, for this simple problem, yes, you could have set that one up directly, couldn't you? What's Newton's second law of motion for this one? Well, you have gravity acting straight down here, mg, goes in the positive direction. Then you have minus the spring force, minus damping force. So just for as a check, yes, it makes sense. Everybody with me on this one? Yeah.
When you were dividing by I, how did mg become only g?
Remember, you divide by I, and I, that's the same as the mass, that's the inertance. So the mass drops. Yeah. So it should be, I mean, each of the terms here has the dimension acceleration, so that would be another control. So yes, the mass has to drop. Let us test this one. Here I have made a small little program for this this problem, and here I have already inserted some numbers. Yeah, let's remove this one. For a real problem like this one, for instance, you are to find a certain behavior. This one should move in a certain way. Okay? Let's say that you know some of these parameters entering this problem, but you don't know all of them. You have to choose. What should the damper be? What should the spring stiffness be? And so on. How to choose numbers. So that is sort of a problem. How to choose numbers. For the different parameters. Initially, when you have done the programming, I suggest you do the following. Just insert 1 for all variables. He is, yeah, that's the initial. Thank you. He can start with 0, that's okay. Can you read this in the back? Or is it too small? Everything is 1, set to be 1. Gravity is 1, mass, spring, and damper. Everything is 1. And now initially I start with 0 p. P, that was the momentum, so mass times velocity is 0. He's standing still. And then I give him q equals 1. So I have pushed him at a distance here. So now let's see if this one works. When you choose everything to be 1, then you will have a time scale in this problem to be around 1. Most of the physics will happen in a time scale of 1. To be certain, I choose a maximum time of 10. Then I should cover most of the physics. Then here, just calculate the p dot and the q dot. P dot should be positive, shouldn't it? Yes, like that. And then negative, negative. And then we try to run this and see what happens. Yeah, that didn't give much. We have gotten an exponential curve here. Never mind that. Why do we have such a strange behavior? It's constant equal to 1. Well, think of the steady state situation here. Steady state, or call it a steady solution. Steady solution, x dot equals x double dot equals 0. No motion at all. Everything is just standing still. What's left then? Okay, here is 0. We have gravity. Here is just a position x, and x dot is 0. Okay, these two terms then has to balance each other. So this will imply gravity equals x times this k over m, or 1 over IC if you like. Okay, so there you see actually the steady state solution. Here everything, although the parameters is set to be 1. So if the initial position is chosen to be 1, then nothing happens. So we just get a constant line. So yes, this looks actually quite promising. So instead of starting with the position 1, let us start with the position 0. And let's see if this changes a little bit. Ah yes, so it did. So it did. So now he starts with the position 0, and then he falls down 1 meters. But he do it in a sort of a wavy motion. But if you continue to simulate, then he should be just constant 1, because we have damping in our system. Say, let's now change the system here a little bit. Remove the gravity. Remove the gravity. Will that change anything? Well, not much actually. So the constant term here drops. Then of course the steady state solution will be 0. So if I now run it, nothing happens. You just get 0 position at all times. So now let us switch and start with a position of 1. That was Q. So I start with a position 1, and then he will find the steady state solution to be around 0. If we now start playing around with, say, the spring here, he was 1, put him to be 0.1. Now we get a more wavy motion here. This dashed line I plotted here, it's actually part of the analytical solution. It's an exponential minus 1/2 RT over I. This will now sort of be the amplitude of the solution. This equation here, it's actually a linear equation. You can find a correct solution for it. So here, analytical solution x of t equals, you will have it like this, a cosine omega t plus b sine omega t, and the entire thing multiplied with e to minus alpha t. This exponential minus alpha t is of course now the damping in the system, and cosine omega t plus sine omega t, that's just a harmonic oscillation. The omega will now be the square root of the parameter you find here, k over m. The alpha we have here will now be 1/2, and then r over m, if I recall correctly. Yeah, 1/2 r over m. And now for this problem, you could use these as choices, like this frequency, for instance. If you want a certain frequency into your problem, okay, then you have to choose the spring stiffness or the mass accordingly. So here you will have a time period equals 2 pi divided by omega. And for this problem here, that should be roughly 2 seconds, 4 seconds, and so on. And if I recall correctly, yes, I have printed it out on the screen, and it should there read something like 2. And it does, 1.98. So frequency, okay, that one you take from the proportional term here with the spring stiffness, depending on how fast you want him to oscillate. The damping, that will now be a choice for this alpha. So say, for instance, you want this amplitude to drop, say, 1 over E for one single time period. How should we write that? Choose R so that the amplitude then of the position X is reduced by 1 over E after the time t equals this time period t to p over omega. For instance, how do you do that? Well, then we have this damping term, e to the power of minus alpha time should be equal e to the power of minus 1. In other words, alpha t equals 1. What was alpha? Alpha was 1/2 r over m multiplied with the time. And now I have chosen a time standing here. So my equation should now read something like this. 1 equals 1/2 r over m multiplied with the time 2 pi over omega. We can keep omega then. The 2 drops. And then we are left with a resistance R equal m omega by pi. So if I choose that resistance, then my signal should have dropped 1 over E after one single period. So let's see if that is the case. We choose this one as a resistance. Let's see. R is not 1 anymore. R equals the mass I multiplied with omega. And then divided by pi. Then I need the omega. I think I had it here somewhere. There we go. So now this one should work. So we drop from the maximum amplitude 1 down to 0.4 after the first period. What is 1 over E? Should be around 0.4 then. 1 divided by E. He doesn't have it. 1 divided by, what is it, 2.7 or something? Fairly close to 0.4. So yes, this will be one way to choose numbers when you have a certain behavior. For exercise 3, when it comes out, you are going to design a shock absorber on a bicycle. And you can imagine then for this damping period. How long should the damping period be? How long time should it take before the motion is dropped 50%, 40%, or whatever? I mean, imagine you go up to a car, and then you put your hands on the hood, and then you press the car down and release it. He will start to move, but quite soon he will stop. It doesn't take many seconds. So then you can tell by the solution from your simulation, how strong damping should I have? Okay, the motion should have been not completely down to zero, but say should be halved in so and so many seconds. So you use this as sort of playing around with the real numbers for your parameters. Also, the period, of course, when you kick a car and it starts to move, how many seconds will it be for one period? Okay, then you have to adjust your omega in your problem. Okay, any questions to that one? For this problem, we were so fortunate that we had an analytical solution to the problem. We have it here. Now, for a real problem, you will not have an analytical solution available, but you will still have in your problem, presumably, some damping terms, meaning you will have something like this affecting your solution. You will have some spring systems, then a natural frequency should pop up. If you don't find them in your expressions, in your equations, then simulate. Then you should see it from the solution. Okay, then you have a frequency of some kind, you will have a damping of some kind. So then you just play around with the simulations, finding suitable numbers. Okay, that was little information about how to find numbers. This is something then you will play around with in exercise 3. Okay, let us take another example. Example, we have here sort of an axis that is up on the ceiling or just fixed in space, and then we put a rod, a solid rod that can then swing back and forth, and this is under the influence of gravity. What we here should obtain is a pendulum. Now, how should we solve that one? The obvious way, sort of straightforward way, would now be to do the following. We are seeking the angle here, the angle phi as a function of time. So if we know this function, then we know everything, then we know the motion. So I want to have an expression involving this angle. He rotates around this point, so he will swing back and forth here, of course. So we are talking a mechanical rotating system. Then how should we think? Well, if you look at the center point of this rod, length L, so in a position L half, there you will have its center point where the gravity will attack. So at this point we can set up gravity. He will act down there. Okay, then we can write immediately the torque acting in this way will now be equal to just this gravity thing, right? So it will be the mass multiplied with the length. That should be L half. But then I want this distance here. Let's see, Lm times gravity, sorry, multiplied with the arm, L half multiplied with, what will it be, sinus of phi. That should be the torque around the rotating point up in the ceiling. I mean, the gravity is constant, but this driving torque is going to change depending on the angle. So how should we do this? How should we start? How should we construct our bond graph? I mean, the driving force in the problem definitely is the gravity. So should I start with a source hitting something? Should we do that? And then let the source be what? It can't be just gravity. That doesn't work. We could use a torque, but then our source will be dependent of the solution. That's not so funny either. So how to do this? How to do this? That is something you can worry about during the break. We take 15 minutes.